Hi, good afternoon, everybody. Yeah, I'm Sandra Young. I'm a PhD student at the University of Brighton, and today I'm going to be talking to you about my research project is my PhD, which is looking into using lexicography to characterise relations between species mentions in the biodiversity literature. So the structure of the presentation today is, first I'm going to explain exactly what I mean by species mentions, so we're all on the same page. Then I will explain the problem and go into what the issue is with looking at the biodiversity literature and species mentions. Then describe the background and the reasons behind taking this approach and using lexicography. And finally, I'll look at some preliminary results from the research. So what do I mean by species mentions? I realize that it could be interpreted in many ways, hence it's good to clarify. So in the research, and I'm looking at the scientific nomenclature, I will also be looking at common species names. So, and the analysis that I'm doing is on token level. So whilst if we're technically talking about species, then you have the genus species, like duality, or even more if you're going to subspecies. When I talk about a species mention, I mean a single token. So that could be, but it could be anywhere on the hierarchy. So you could go up to chordata, all the way down to families like Salmonidae, genera, or including things. I'm looking at common names as well than any of those, but it's a specific token that I mean. And so with the issue with biodiversity, then biodiversity has a very long history of recorded heritage, which started when people started to describe species, which is what's developed into today's taxonomy, the study of taxonomy. That also includes areas such as ecology and biodiversity and biology. And as with many other areas, then ontologies are very popular forms of knowledge representation when they're trying to collate all of this data. However, because of a specific aspect of the biodiversity literature, then some researchers have questioned the suitability of ontologies to represent specifically biological taxonomies. So to explain a little bit, then there is no one accepted biological taxonomy. It's the idea of the hierarchy of life that comes down from one original species, and they're made up by finding a physical specimen, describing it, and then this species is assigned a scientific name according to the scientific nomenclature. So this is the linguistic representation of that physical specimen. However, this is a theory. It evolves with scientific knowledge. So as DNA, to give an example, as DNA analysis evolves, then they may change the definition of this what is called the taxon, and this impacts on the scientific nomenclature. And so not only do you have this biological taxonomy that's constantly evolving, the linguistic representation of this also does, which leads to lots of synonymy, lots of homonymy, and just changes. So to give you an example, then you have the word melpomene, which is simultaneously a genus of spiders, a genus of ferns, and the species level name for it's Heliconius melpomene, which is a postman butterfly. And when I was looking for these pictures, then I was speaking to the man that took the fern picture, who's a fern specialist. And he was talking about in the checklists, there's a checklist that is frequent, where he uses anyway. And because of the issue with these namings, then they now, to search for melpomene, you have to go through an accepted synonym that specialists know about but nobody actually uses. And this is one of the reasons that this ambiguity is a problem, because the scientific nomenclature is often used as an index for all of this biodiversity information. And so with it changing, there are questions as to whether things are being combined as if they were the same thing when really they're not. Or things are being separated out in ways that they shouldn't be. So, in my research, then, the idea is to adapt lexicography techniques to perform an empirical evaluation of nomenclature use in a specific corpus, and then be able to use this to compare with existing ontologies to see if everything actually matches up and there maybe isn't so much of a problem, or if there are interesting differences. And so why lexicography? So corpus-based analysis is already used in automatic ontology creation and verification, and lexicography uses corpus analysis to look at the patterns of language use in context. However, it's very flexible, whereas ontologies have this formal logic which could impede these changing meanings of the nomenclature because there are seemed inconsistencies. With lexicography, you don't have that problem because it is accepted that words are fluid and flexible. They have multiple meanings and they change depending on the domain or the time in which they're used. The query tool that I'll be using, the corpus query tool, is called Sketch Engine. And I chose this tool specifically because it has a feature called word sketch, which when you're making a dictionary, it's, I think the next slide, yeah. So this is an example of a word sketch. So you're trying to create a dictionary entry and you want to look at the way that it's used in context. And these word sketches are made up of two aspects. You've got linguistic pattern matching through corpus query languages like regular expression rules, which denote the different grammatical patterns and the different grammatical relations between different words. So here you can see mine as a verb, and it's object and subject when it does this. And then with the collocations, then you see the semantic areas in which a word is used. And with the case of mine in this corpus, you can see that there's a clear distinction between the extraction of physical elements from the earth with things like ore, gold, and coal, and then the extraction of data with things like database, datum for data mining, and algorithm. With my methods, then I'm currently looking at freshwater species. So I gained access to the Journal of Ecology of Freshwater Fish through the university subscription to Wiley, so it's not open access data. It's a corpus of 3.5 million tokens, and yeah, I accessed it through the API, through the text data mining agreement, and pulled down the PDFs that I then OCR'd using Ant Converter by Anthony Lawrence. And then once I had this data, then in order to be able to adapt the word sketches to pull out the information that I was interested in. And then first I added some semantic annotation relating to species mentions. So there were scientific names that I identified, and this was identified through an existing API, which is called Global Names Recognition and Discovery, which you can find in the paper in the conference proceedings. You can find the details, or I can tell you that. And then the common names and also general collective terms and life stages, which I was mainly using for another part of the research, but these were identified through corpus analysis techniques looking at key terms in the specific corpus. And then I adapted the sketch grammars, so the linguistic patterns, to only look for collocations which involved these entities. I also limited the relations that were actually included. I used an extended form of the sketch grammar, which is through ecolexicon, which is another initiative that has been developed through Sketch Engine. And these are the relations that I identified, and I identified child-parent relations according to the semantics of these relations. To actually start to work with the word sketches in a way that I could visualize them and start seeing the links and if there are any hierarchies being identified, then I pulled out all of the word sketches from Sketch Engine. This was done into an XML file, so this is an example of one XML for the keyword anguilla, and then you've got all of the different collocations. This, I amalgamated all of these together according to their parent-child relations and added up the hits and the scores. So with the hits, then that's the frequency of times that a relation appears in the corpus, and the score is something called a salient score, which is the importance of a relation in context. This is hoped that in a future part of this research, this could be interesting because it works on the idea that lexicons have a very long tail distribution, and so does scientific nomenclature, and the salience score is based on finding important relations despite their infrequency, so it overrides some of the need for such frequent hits. And that is also described further in my paper. So in the results then I've done some filtering for frequency and also for salience, because when without any filtering or salience, then this is the graph that comes out. It's obviously quite difficult to read. So if I was looking for frequency of hits over 20, so relations that only appear more than 20 times in the corpus, then this is, in this I'm looking at the Salmodidae family, because it was the relations that came out relating to the Salmodidae family were the most frequent in the corpus, so there were more interesting relations to be found. And so you can see there are three genera relating to the Salmodidae family in this frequency over 20, and as you can see, the arrows indicate that it's a parent-to-child relation, and all of these surrounding ones on each are, well, apart from par, which is a general term, but they are species level mentions of these genera. You can also see with the green squares where you've got common names, and whereas you can see trout is linked to all three different genera, but just some species. At the moment, salmon is only linked to the Salmo genera. If we look at frequency over 10, then it is a little bit more messy in a way, but it's mainly added further links to further different species mentions. And you can also actually see now that the common names salmon and trout are both related to different species of various genera. So there isn't a clear distinction between certain species from certain genera and a common name. It's actually very much it's all a big mix. So this is useful to be able to disambiguate common name usage amongst the nomenclature, if I can speak. And then finally, just a quick look at the preliminary salience filtering. Then salience filtering, because it maintains sometimes infrequent but important, it can be important relations, then you keep the whole big graph for a lot longer. You have to raise the salience a lot higher. You tend to have a more linked graph than you do with frequency. And here I just wanted to show the fact that I chose frequency over 50 and salience over 11, because they had nearly the same number of nodes, but salience had just had one node less, but an extra edge, so an extra connection. So you can still see salmon, and also you see a different emphasis, because whereas here salmon is already only just connected to salmo, whereas trout is still a central part of the linking different aspects of the graph. Here, salmon maintains, in the salience, salmon maintains more links between different genera. So with conclusions, these are just the preliminary results of what I've been finding. I've been continuing to, I've identified that hierarchies can be identified in the species mentions using adapted word sketches. We can see from the preliminary results that filtering options differ in the relations highlighted, and that common name usage across the scientific nomenclature could be disambiguated using this technique. And so with my next steps, then I'm looking at identifying specific characteristics of graph nodes for evaluation purposes, seeing if in specific parts of the graph, then there are characteristics that mean you can say that something is either a specific rank in the hierarchy of species, or if you know that if you can see comparative ranks. Also developing an automatic evaluation of this data compared to existing ontologies. And I want to look further at contrasting qualities and uses of frequency versus salience filtering. And then hopefully I'll get to test the corpora on the following results on corpora with known ambiguities relating to nomenclature usage. So thank you. And any questions?
Thank you very much. Any questions? It's really Friday afternoon. Okay. Thanks for that talk.
So I've got just one question about the networks that you've shown. So each of those links is actually any of the relations that you've shown for the child-parent relations, or like?
Yeah, because so as in, right, let's see. So you mean any of these? Yes. Yeah. I mean, I've really simplified it down and amalgamated. So if it was parent, child, then it didn't matter whether it was now modified or if it was have part or any of those.
Yeah.
You might have some issues with that.
Sure.
In my choice with that.
The idea is that people have worked for now like 5-10 years on something that's called multi-layer networks, where you have a couple of layers of networks that represent different types of relations. And then, so they've met methods of ranking the nodes in those networks, or parsing those networks, and so on. So, I mean, maybe there are some methods already.
That I could use, no, that would be really, so you say multi-layer networks?
Yeah, multi-layer or multiplex networks, so a couple of different ways.
Thank you.
Any other questions?
Thanks for this, very interesting. I just wondered if, you've got a particular corpus, but there's a lot of work being done with herbariums and this sort of things, and I just wondered, the disco, is it disco? I'm just trying to look what it meant. But it's, that is a sort of European infrastructure for natural history collections, and I just wondered if the sort of corpus kind of stuff
that they
could be compared with the metadata that they've done.
That would be really interesting. I mean, with the herbariums and things like that, then they tend to be looking at actual taxonomic descriptions, which I was deliberately not looking at because of the way that the language works there and the way that it is. But it would be really interesting to see how they do compare, or if there's anything that could be done here.
Anybody? Okay.
Yeah, thank you.
Very much.